Welcome viewers. In this video we'll see the capacitance of two-wire transmission line. This is the overhead transmission line having the two conductors, so the single phase power can be transmitted through this transmission line. It is a overhead transmission line. So by referring the diagram, we have the two conductors, conductor A and conductor B. Conductor A is positively charged and conductor B is negatively charged. Our aim is to find the capacitance between these two conductors, conductor A and B. The radius of the conductor is R meter. Radius of each conductor is R meter. The center to center distance between the conductor is D meter. The center of conductor A to center of conductor B is D meter. The point P is located. We are having the point P at a distance X meter from the center of the conductor A. The point P is available at a distance X meter from the center of conductor A. Conductor A is taken as reference conductor. Then the distance between point P and center of the conductor B is D minus X. Right? So this will be X, this will be D minus X. The distance between center of conductor A to outside of conductor B is D minus R. So during the integration, we need a limit. So the limit is decided by two parameters. One is radius of the conductor. Another one, this D minus R, center of the conductor A to outside of conductor B. So this distance will decide the another limit of the integration. Right? So we have conductor A and B. Center to center distance is D meter. Radius is R meter. Point P is located at a distance X meter from the center of conductor A. The distance between point P and center of conductor B is D minus X. The point P is available. EA and EB is nothing but electric field intensity due to conductor A and conductor B. Now we are having the Gaussian cylindrical surface. We are assuming on Gaussian cylindrical surface with radius X meter. We are assuming that here one cylindrical surface is available, X meter, and the height is 1 meter. We are assuming 1 meter length of cable, right? So the Gaussian cylindrical surface with the radius X and height 1 meter. Similarly, if you refer conductor B, we have another Gaussian cylindrical surface with the radius D minus X, right? If you refer A, X, if you refer B, D minus X. So there are two conductors available. Right? So the total capacitance, this is the total capacitance, is nothing but capacitance due to conductor A and capacitance due to conductor B. Both are connected in series. Right? So this C dash is the capacitance due to conductor A. This C dash is capacitance due to conductor B. Right? So due to both are connected in series, the total capacitance C is C dash dot C dash divided by C dash plus C dash. So that is equal to C dash dot C dash divided by 2 C dash. By adding these two, we got 2 C dash. So 1 C dash got cancelled. So the C dash divided by 2. Right? So C equal to C dash divided by 2. From that, C dash equal to 2 into C. The capacitance per conductor equal to 2 times of total capacitance. C dash equal to 2C. So we will find both C as well as C dash, total capacitance as well as capacitance due to the conductor, per conductor. Here the description is available. The conductor A and B are uniformly charged with plus lambda by coulomb and minus lambda by coulomb respectively. Right? Conductor A is positively charged, conductor B is negatively charged. Due to length, we are using linear charge density, plus lambda and minus lambda. Radius of each conductor is R meter and separated by D meter. We are considering the point P at a distance X meter from the reference. Reference is nothing but conductor A. Then the distance between conductor B and point P is D minus X. EA and EB are the electric field intensity due to conductor A and conductor B. Now we will apply the Gauss law to find the electric field intensity due to conductor A. Right? By using Gauss law, we will find So we are having the imaginary cylindrical surface with height 1 meter and radius x meter. We consider one imaginary cylindrical surface. So the general formula for E equal to Q divided by 4 pi epsilon r square is the general formula. So that can be rewrite as Q divided by epsilon 4 pi r square. Since 4 pi r square refer the sphere. Normally we refer the charges are in the form of sphere. But here we are using cylinder. So that this term is replaced by area of the cylinder 2 pi RH. Especially in this derivation we are using cylinder. So that this term is replaced by 2 pi RH. In this r is nothing but x. The radius is x and the height is 1 meter. So that what we got Q divided by 2 pi epsilon x. So the electric field intensity for this cylindrical surface is Q divided by 2 pi epsilon x. For other cases we can use this directly. Right? Because of cylinder it is replaced by this value Q divided by 2 pi epsilon x. Now we have the two electric field available. So the total electric field equal to EA plus EB. Electric field due to conductor A plus electric field due to conductor B. So that is Q divided by 2 pi epsilon x. That's available here. While referring conductor B, Q divided by 2 pi epsilon d minus x. Because the conductor B and the distance between the conductor B and point P is d minus x. Right? So conductor A located at a distance x meter, conductor B located at a distance d minus x. Now this Q divided by 2 pi epsilon is constant. Constant between these two, commonly available between these two, we can take outside. So what we got, Q divided by 2 pi epsilon 1 by x plus 1 by d minus x. Right? Now we got the expression for electric field. From that we will go to potential. From the potential we can find the capacitance. Then what is the relation between the electric field and potential? E equal to minus dV by dx. So that dV equal to minus E into dx. From that, by integrating on both sides, V equal to minus integral E dot dx. This is a standard formula. V equal to minus integral E dot dx. From that we can find the expression for potential. Now we'll see what is the limit for this integration. So the potential difference between A and B is defined as work done in moving a positive charge from B to A. Right? So the potential difference is nothing but work done. For the what is work done? Moving a positive charge from B to A. So the electric field lies between the surface of conductor A and B, that is d minus r to r. Right? The distance between the conductor outside d minus r and radius of the conductor r, that will decide the limit for this integration. So we are using the limit d minus r to r. So that V equal to minus, the substitute the limit d minus r to r Q divided by 2 pi epsilon into 1 by x plus 1 by d minus x into dx. Now these limits are substituted and E value is substituted. So this Q divided by 2 pi epsilon is constant, that is taken outside, minus Q divided by 2 pi epsilon integral d minus r to r 1 by x plus 1 by d minus x into dx. Now we can go for simplifying the this integration. So while simplifying, Q divided by 2 pi epsilon is there. So the 1 by x, integral 1 by x is log x. Similarly, 1 by d minus x is log d minus x, but here minus x is available. Again we need to differentiate. Differentiating minus x is minus 1. If it is d plus x, no problem. D minus x is there. We are integrating with respect to x. So we need to take the differentiation of minus x again. So that will give minus 1. Right? With a limit d minus r to r. So integral 1 by x is log x. Integral 1 by d minus x is log d minus x. But here minus x is available. By differentiating this minus x, we are getting minus 1. Right? Now we can substitute the limit. q divided by minus q divided by 2 pi epsilon log x. So this minus 1 become this minus negative minus log d minus x d minus r to r, right? The term become minus. Now we'll substitute the limit one by one. Minus q divided by 2 pi epsilon, we substitute these limits log r minus log d minus r. First the upper limit is substituted log r minus log d minus r. Then substitute the lower limit minus. While substituting lower limit we got minus log d minus r. Here already one minus is there, so it become plus log d minus this x. X is nothing but minus log d minus of d minus r, right? This x is replaced by d minus r, right? So log r minus log d minus r, upper limit, log d minus r plus log d of d minus r, this lower limit, right? This negative is there so that it become positive. Now we can go for further simplification. So log r minus log d minus r minus log d minus r plus log, you can multiply inside d minus d plus r, d minus d plus r. While multiplying this negative inside, what will happen? It become minus d. The already one minus is there, so it become plus r. So this d got cancelled, right? Now what we got? Log r minus log d minus r minus log d minus r into this plus log r, right? See this log r available 2 times, log d minus r also available 2 times, so we can add these two values. So 2 log r minus 2 log d minus r, right? Now we can take these two outside, right? Already one 2 is there, so got cancel. Log r minus log d minus r, right? So that what is there? Q divided by pi epsilon log d minus r by r, log r, right? So the negative available outside, that is multiplied inside, so that these two values are interchanged. This become negative, this become positive, so that log d minus r minus log r, right? What is log d minus r minus log r? That is nothing but log d minus r by r. Log a minus log b is nothing but log a by b. By using that we can find this. So that finally what we got? V equal to q divided by pi epsilon log d minus r by r, right? Now we got the expression for the potential, but our aim is to find the capacitance between the conductors, right? Okay, so that we are substituting q equal to cv. We are replacing q by cv, so that v equal to this q is there, q is replaced by cv divided by pi epsilon log d minus r by r. So this v got cancelled, right? So bring this term in the numerator, bring this term in the denominator, so that c equal to pi epsilon divided by log d minus r by r, right? So this term is brought into numerator, this term is brought into denominator, that is equal to c, right? So what we got? C equal to pi epsilon log d minus r by r, the final expression. What is the unit? Farad per meter. Because we consider only 1 meter length of cable, so that the unit is farad per meter. Pi epsilon divided by log d minus r by r. So this is the total capacitance. What is the capacitance per conductor? C dash equal to 2 times of C, 2 times of total capacitance per conductor. So that is C dash equal to 2 times of this C, right? 2 into C, 2 pi epsilon divided by log d minus r by r, right? So this is the capacitance due to conductor, single conductor, so that unit is farad per meter per conductor, only one conductor. Here we have C dash refers only one conductor, right? So 2 pi epsilon log d minus r by r farad per meter per conductor, right? So this is total capacitance. This will be capacitance due to single conductor. In both the cases we assume 1 meter length of cable, right? Now we got the expression for total capacitance as well as capacitance due to single conductor. Now we'll solve two problems. First we'll go to the first problem. In this first problem, calculate the capacitive reactance Xc of a single phase 50 Hz transmission line of 100 km with two parallel lines of 1 cm diameter wire with 3 meter diameter apart in free space. Right? So we need to find the capacitive reactance for a single phase transmission line. The frequency is 50 Hz. The length is 100 km, that is 100 into 10 to the power 3 meter. The distance between the conductor is 3 meter. The diameter is 1 centimeter, so that radius equal to 0.5 centimeter, that is 0.5 into 10 to the power minus 2, that is 0.005 meter. Right? Now these are the data available. Frequency available, length of the conductor available, distance between the conductor available, diameter, thereby radius available. Epsilon naught is nothing but 8.854 into 10 to the power minus 12. Right? That value also available. Now we'll find the capacitive reactance. If you want, the capacitive reactance formula is 1 divided by 2 pi Fc. This is a formula. Here F is already available, 50 Hz. But C value is not given. So first we will find the C value. If after calculating C value, we can calculate the capacitive reactance. Right? What is C value? Pi epsilon naught epsilon r divided by log d minus r by r. Just now we got this derivation. This is a total capacitance C. Pi epsilon naught. So the pi into epsilon naught is 8.854 into 10 to the power minus 12. Epsilon r is 1. We are assuming that it is a air. Divided by log d minus r. D is distance. Distance between the conductor is 3 meter minus radius is 0.005 meter divided by 0.005. Right? So this is a natural log. Base E. You have to consider the base E, not a base 10. It's a natural log into 100 kilometer. You have to multiply with the length of the conductor. Right? 100 kilometer. So 100 into 10 to the power 3. So now all the values are substituted. The final C value is 0.434 into 10 to the power minus 6 farad. Now we got the value of capacitance. From that we can find, by using this capacitance, this formula, we can find the capacitive reactance. So the capacitive reactance Xc equal to 1 divided by 2 pi Fc, that is equal to 1 divided by 2 into pi into the frequency is 50 Hz. The capacitor value is 0.434 into 10 to the power minus 6. Right? After simplifying, what we got? The capacitive reactance Xc equal to 7.334 kilo ohm. Because of the reactance, it is given as ohm, kilo ohm. Right? That is 10 to the power 3. 7.334 kilo ohm. Right? So for calculating capacitive reactance, we first calculated the capacitance. From that we calculated the capacitive reactance. Now we'll go to the one more problem. Two parallel long conductor have provided a capacitance of 20 picofarad. The capacitance value is given. This is also two-wire transmission line. The capacitance value is 20 picofarad. The center to center distance between the conductor is 1 centimeter. The center to center distance also given, 1 centimeter. What is the question? What size of conductor, what size of the wire should be used when epsilon r equal to 1? Right? What does size mean? Radius. We need to find the radius of the conductor when epsilon r equal to 1. First division. In the second division, what size of wire should be used if it is placed in a sea water? Through the transmission line is placed in a sea water. In that case, epsilon r equal to 2. Right? So first case epsilon r equal to 1, second case sea water, that is epsilon r equal to 2. Right? So first we will write the data. So we are having the capacitance value 20 picofarad. 20 picofarad means 20 into 10 to the power minus 12 farad. The center to center distance is available 1 centimeter, means 1 into 10 to the power minus 2 meter, that is 0.001 meter. Right? 0.001 meter. Then epsilon naught is constant 8.854 into 10 to the power minus 12. So these are all the data available. First we will consider the first case epsilon r equal to 1, right? What is the formula? C equal to pi epsilon naught epsilon r divided by log d minus r by r. So just now we got the derivation, capacitance of a two-wire transmission line. So this r is the question. We need to find what is the size of the wire. Size of the wire means radius of the wire. Other data are available. Capacitor is available. 20 into 10 to the power minus 12 farad, right? It's not 2, it's 20. 20 into 10 to the power minus 12 by epsilon naught is 8.854. The epsilon r is 1 divided by log d minus r, 0.01 minus r by r, right? So now this r value we need to find. Bring this term here and bring this 20 into 10 to the power minus 12 in the denominator. So log 0.01 minus r by r equal to this value divided by 20 into 10 to the power minus 12, because this value is not known. We need to find. So by simplifying this, what we got? 1.39. So the log to the base e 0.01 minus r by r equal to 1.39, right? Then how will you find the radius from this expression? What is the how to find that? So here one example is available. Log base e a equal to x means that can be rewrite as, you have to interchange these two values. E power x equal to a, that is we are removing the log, right? For how to remove this log, we need to interchange these two values. E power x equal to a, so that we can remove the log value. E power x equal to a. Like that, you have to bring this value here. E power 1.39. Bring this value here. 0.01 minus r by r, right? So based on this formula, interchanging these two will remove the log. Here we are doing the same. We are using the same formula. E power 1.39 equal to 0.01 minus r by r, right? So e power 1.39 is 4.014. That is equal to 0.01 minus r by r. Now cross multiply this. 4.014 r equal to 0.01 minus r, right? Bring this r that side, so that 4.014 r plus r equal to 0.01. So these two are added. 5.014 r equal to 0.01. So r equal to 0.01 divided by 5.014. From that we calculated r equal to 1.994 into 10 to the power minus 3 meter. That is r equal to 2 millimeter. Right? R equal to, by using this we can find r equal to 2 millimeter. So first case, the radius of the conductor, size of the conductor is 2 millimeter. Now we'll go to the second condition, epsilon r equal to 2. Same problem, only we need to find, substitute epsilon r equal to sea water. C equal to pi epsilon naught epsilon r divided by log to the base e d minus r by r. The C value is substituted, epsilon naught is substituted, pi, the epsilon r equal to 2, log to the base 0.01 minus r by r. Right? This value is not known, so exchange these two values. Bring this value in the numerator, bring this value in the denominator, so that log 0.01 minus r by r equal to this value, right? Now we can simplify this. So while simplifying, what we got? 2.78 log 0.01 minus r by r equal to 2.78. So based on the previous value, we can interchange these two. E power 2.78 equal to 0.01 minus r by r, right? So the value of e power 2.78 is 16.119. That is equal to 0.01 minus r by r, right? Now multiply this r in the numerator. So 16.119 r equal to 0.01 minus r. Bring this minus r in the left hand side. So that 16.119 R plus R equal to 0.01. So 17.119 R equal to 0.01. So that R equal to 0.01 divided by 17.119. Right. So by simplify this, what we got, 0.00584 meter. That can be written as 0.584 into 10 to the power minus 3 meter. Right. So for epsilon R equal to 2, we got the value of R, that is the size of the conductor is 0.584 into 10 to the power minus 3 meter.